Every Git repository hides a secret world inside a folder called .git.
I've seen that folder before, but I always thought it was just magic I shouldn't touch.
That's exactly the misconception we're here to fix. .git is just a directory, no magic, just structure.
So what's actually inside there?
The head file, the config, the objects directory, refs, the index, hooks, and logs. Each one has a specific job. Once you understand these pieces, Git stops being a black box and becomes a tool you truly command.
So you're saying if I understand .git, I'll never be afraid of a merge conflict again?
You'll still hate them. But you'll understand what's actually happening under the hood. Let's start with the simplest file in .git, head. It's just a text file.
A text file? That's it? I thought head was something complex.
Open it up and you'll see something like refs heads main. That's a symbolic reference, a pointer to a pointer.
So head points to a branch, and the branch points to a commit.
Exactly. That indirection is what lets you switch branches so effortlessly.
And detached head? I've seen that error message and it sounds terrifying.
Detached head just means head points directly to a commit hash instead of a branch name. You're not on any branch, but you're still safe.
So it's not a bug, it's a feature?
Classic Git. Just create a branch to attach head again and you're golden. The config file is Git's memory. It stores your identity, preferences, and remote repository URLs.
Is that why Git always asks for my name and email on the first commit?
Yes. Every commit stamps your identity. Config can live in 3 places: system, global, and local.
System, global, local, that's 3 levels of configuration?
Local wins over global, global wins over system. Project-specific settings override your global defaults.
So if I want a work email for one repo and personal for another, local config is the answer.
Exactly. And that's where your remote origins live too, the URLs Git uses to push and pull.
So I could technically edit .git config by hand instead of using git remote?
You could. But the commands exist so you don't accidentally break your repo with a typo. Now we enter the objects directory. The simplest object is called a blob.
Blob? Like the thing from a sci-fi movie?
Binary large object. It's just your file content, nothing else. No file name, no permissions, no metadata.
Wait, Git stores my file content without even remembering the file name?
Correct. Git runs your content through SHA-1 hashing and uses that hash as the file name. That's content-addressable storage.
So if 2 files have the same content, they share the same blob?
Now you're getting it. That deduplication is one reason Git is so incredibly efficient.
So the hash is basically a content fingerprint. That's actually brilliant.
You can try it yourself. Run Git hash object on any file, the hash you get is its blob identifier. If blobs are the content, tree objects are the directory structure that organizes them.
So a tree object maps file names to blob hashes?
Exactly. Each tree entry stores a file mode, a file name, and a pointer to either a blob or another tree.
Pointer to another tree, so that's how subdirectories work?
Precisely. A directory becomes a tree object that contains blobs and nested trees. It's a hierarchical file system snapshot. Those file modes you see, like 100,644 for regular files and 100,755 for executables, are stored right here.
So the tree is what gives structure to the flat blob storage. Blobs are nouns, trees are the grammar.
That's a great analogy. Trees and blobs together form the content layer of Git. Now we reach the commit object, the star of the show. A commit is just another object in the database.
Wait, commits are objects too? Like blobs and trees?
Yes. A commit object contains a tree hash, 0 or more parent hashes, author info, committer info, and a message.
The tree hash, that's the snapshot of the entire repository at that point?
Exactly. The tree points to blobs and subtrees, so one commit gives you the entire state of every file.
And the parent hash, that's how Git knows the history chain?
Right. The first commit has no parents. Most commits have one. Merge commits have two or more.
So a commit is really just a snapshot with some bookkeeping attached.
That's all it is. Simple, elegant, and incredibly powerful once you see the whole picture. Here's the biggest mind shift: a branch is just a text file containing a commit hash.
Wait, that's all a branch is? A single line in a text file?
Look inside ref/heads. Each file is a branch. Its content is the hash of the latest commit on that branch.
So creating a branch is literally creating a new file?
Yes. Git branch just writes a hash into a new file. Switching branches updates head to point to that file.
And deleting a branch just removes that file? That's it?
That's it. But the commits themselves are still there. That's why you can sometimes recover a deleted branch.
My whole mental model of branches just collapsed and rebuilt itself. Thank you.
Tags are like branches that never move. They're permanent markers in your project history.
I've used tags for releases. Is there more to them?
There are two types, lightweight and annotated. Lightweight is just a pointer, like a branch that doesn't move.
And annotated tags?
An annotated tag creates a full object in the database with a message, date, and the tagger's identity.
So annotated tags are like commits but for tagging? With a full object?
Exactly. They're cryptographically signed too if you use GPG. That's how projects verify release authenticity.
So tags are like bookmarks that say this moment matters, while branches chase the latest code.
Perfect summary. Tags are history's anchor points. The staging area, also called the index, is one of Git's most misunderstood features.
GitHub puts files in the staging area, but what is that actually?
It's a binary file at .git/index. A sorted list of tracked files with their blob hashes and metadata.
So Git writes a blob and updates the index?
Exactly. Git hash objects your file into a blob, then records that hash in the index with the file name.
And Git commit snapshots whatever the index looks like?
Yes. It creates a tree from the index and wraps it in a commit. The index is the proposed next commit.
So the index is a preview of the next commit. That makes much more sense now.
Try Git ls files stage. It's eye-opening. Ever made a commit you regretted? The reflog is your safety net.
The reflog? I've heard of it but never understood how it works.
It's in .git/log/head. A simple file logging every commit, reset, checkout, and merge.
So even if I reset, the old commits are still in the reflog?
For a while. Entries expire after 90 days. During that window, nothing is truly lost.
So I can travel back in time?
Git reflog shows where head has been. You can use those references to recover anything.
That reset hard I did last month. I could have fixed it?
The reflog is Git's way of saying I've got your back. Merges are where Git's object model shines. A merge commit is just a commit with multiple parents.
Multiple parents, that's the key difference?
Yes. Git walks both histories and combines them into a new snapshot tree.
So the tree is the combined result of both branches?
Exactly. If both branches modified the same file, Git stores conflict markers in the index.
Conflicts live in the index? Not in my working files?
The working files get the markers so you can see them. The index stores all three versions, base, ours, and theirs.
3 versions in the index. So merge tool reads from there?
Exactly. Merges are just clever object graph traversal. A pack file combines many objects into a single file with a corresponding index. But the real magic is delta compression.
Delta compression?
Instead of storing every version of a file, Git stores one version and then stores only the differences for subsequent versions.
So Git GC is like defragmenting and compressing the whole database in one go?
Exactly. Git GC packs loose objects, prunes unreachable ones, and applies delta compression. It's maintenance mode. You might wonder why your .git folder isn't enormous despite thousands of commits. The answer is packing.
Packing? You mean Git compresses the objects?
Individual objects are stored as loose files using zlib compression. But over time, Git packs them into pack files.
What's a pack file?
Hooks are scripts Git executes at key moments. They live in .git/hooks and they're incredibly powerful.
I've seen the .sample files in there. Are those the hooks?
Those are sample scripts. Git doesn't run them until you remove the .sample extension and make them executable.
So I could write a script that runs before every commit?
That's the pre-commit hook. It can lint your code, check for secrets, or prevent commits to the main branch.
And if it fails, the commit is rejected?
A non-zero exit code aborts the operation entirely. Hooks give you total control over your workflow.
So pre-commit CI and Husky are just managing these shell scripts for me?
Exactly. They're automation wrappers around the same hook system that's been in Git since day one. Let's walk through Git add and Git commit, step by step, object by object.
I'm ready. Show me the pipeline.
Step 1. You modify a file. Git detects it because the timestamp doesn't match the index.
So Git constantly compares the working tree to the index?
Exactly. Run Git add. Git hash objects the file, stores the blob, and updates the index.
So the blob exists, but there's no commit yet?
Correct. Now Git commit creates a tree from the index, then wraps it in a commit object.
And the commit gets the current head as its parent?
Yes. Then Git updates the branch ref and the reflog. Your commit is now in the permanent object graph.
So the pipeline is, working tree, git add writes a blob and updates index, git commit creates a tree and wraps it in a commit, then updates the ref. That's elegant.
Now every Git command will make sense at the object level.
I feel like Neo seeing the Matrix. Thank you for this deep dive.
Every Git object, blob, tree, commit, or tag is stored on disk using a simple two-level directory scheme.
Two-level? What does that mean?
The first two hex characters of the hash become a directory name. The remaining 38 become the file name. Hash E69 to 29b becomes .git app objects E69 to 29b.
So there are 256 possible directories, from 00 to FF?
Exactly. It's a fan-out strategy. A single directory with thousands of files is slow on most file systems. Spreading across 256 keeps each directory small and fast.
That's a cleverly simple solution to a scalability problem.
That brings us to the end of our Git deep dive. I hope you now see .git not as magic, but as a beautifully simple system.
This was incredibly eye-opening. Thanks for taking us through it.
If you enjoyed this video, don't forget to like, share, and subscribe to SRK Master Stack for more deep dives.
See you in the next one. Keep coding.